So the thesis of this talk is that the industrial sector is missing out on a lot of the key benefits of the Internet things, all the exciting buzz and miniaturization and new technologies. The reason for that is that a lot of the kind of the big players, you know, the power plants and the factory floors of the industrial sector are bogged down by very old legacy equipment, these big workhorses of technologies that have very slow hardware update cycles. Often they're not upgradable for much more fundamental reasons. So today we're going to be looking a little bit actually at the nuclear power sector, a lot of which was constructed way before RF technology such as Wi-Fi was in regular use. And the problem with a lot of this technology, not only is it hard to upgrade, but it's actually often living in environments where radio frequencies are not permitted. So in the nuclear environment, in the medical environment, EM-based communications are simply not permitted because of the potential for interference between devices. And the cost of upgrading these devices is prohibitively expensive. There are a couple more issues within industry, namely the huge spectrum of platforms, proprietary and legacy communication systems, and also the fact that the sites, the physical plants that the operators are moving around in are often distributed over really wide areas in big concrete buildings laced with metal, which makes it very difficult and expensive to deploy Wi-Fi in a lot of these situations. There's also the issue of localization, so as an operator is walking through a building, it's sometimes less than trivial to know where they are. They're having to, enter coordinates or write down coordinates manually. One of the problems that we're trying to tackle is actually that idea of solving location management. Interacting with devices that are nearby to me, effectively. So today we're going to talk quite a lot about a company that we, as Chirp, have been doing some prototyping with, and that is EDF Energy, who are one of Europe's largest energy companies. They operate 8 nuclear power plants across the UK, 55 more widely. And some of the builds of these factories date back from the mid-50s, before even walkie-talkies were in regular use. And for this reason, it's very difficult for these guys to use radio frequency in particularly safety-critical areas. It's simply prohibited because the potential for interference is too great, and obviously the risk is tremendous. There's a huge risk there. There's also a huge expense there in deploying cabling, in that it involves cutting through these large safety-critical structures. And the other factor that has to be borne in mind by these big operators is the huge expense of downtimes. If an error or a problem takes place in one of these plants, the cost of downtime can stretch to £800,000 a day per reactor or more in some cases. And this means that, you know, maintaining reliable operation becomes somewhat of a big issue. The solution that we're going to be talking about we call acoustic networking. And this is similar in some ways to radio frequency networking. We have a medium. In RF technologies such as Wi-Fi and Bluetooth, we have EM waves. In acoustic networking, we're simply using sound waves, so the vibration of particles through the air in the same way that you can hear what I'm saying at this very moment. And of course, this kind of technology actually has a really long-standing heritage. Within the communications world. This sound should be familiar to many of you. So we've got DTMF tones, dialing a number. Then we have a modem negotiation sound, a modem or fax negotiation sound. So we have 2 different devices negotiating a connection with each other and transmitting information that's mapped onto effectively a series of frequency values. So it's taking a numerical value and mapping it to an auditory value that then gets received at the other end and decoded. And I mean, this dates way back, way before dial-up modems. Even in the 1800s, Morse code was used in the very early days of radio telephony. So sound, in some ways, is really the granddaddy of all of the complex, sophisticated communications media that we're using nowadays. What we're trying to do nowadays, as are a few others in the field, is try and update this technology for the age of IoT. So no longer are we sending information down cables necessarily. We might be sending information from an embedded sensor to a tablet, or from a machine to another machine. And that is often happening in geographical proximity. And the networking technologies that are traditionally used by the internet, TCP/IP and so forth, weren't really designed for this kind of bandwidth constrained, geographically located communication. Whereas sound is kind of powerful for this, because it means that I can communicate just with those devices that are nearby to me. So if I'm in the kitchen, I can say, turn on the kitchen lights. And by virtue of me being there, the sound is bounded by that space and can only operate those devices around me. There's a whole series of affordances of sound that make it particularly powerful for the realm of IoT. The biggest of which is that it's ubiquitous. So there's tens of billions of loudspeakers and microphones in the world. You know, any low-end device, even an old feature phone, is equipped with the ability to send information over sound, things that way predate Bluetooth and this kind of more modern technology. This also means that it's very safe in terms of being a fail-safe technology. You know, it's almost lowest common denominator. When other technologies can fail, sound in a way is kind of bulletproof. It's very simple in terms of its technological requirements. It's also simple in terms of establishing a connection between two devices. So unlike Bluetooth, which requires pairing, or connecting to a Wi-Fi network, which requires entering credentials, with sound, all you need to do is begin generating tones into the environment, and anything nearby can then immediately detect and decode those tones and obtain the data that is contained within them. And that brings me on to the fact that sound is broadcast. So unlike a paired Bluetooth connection, if I play a piece of audio into this room, all of your devices can receive it instantly without having established any prior connection. So it's one-to-many by its kind of natural foundation. And it's also tangible, which is an interesting one. So unlike a radio frequency communication, we can hear if a communication is taking place. And in the consumer realm, that's actually quite an appealing thing, because it makes it very intuitive. You can hear that communication is taking place. There's a trust relationship, and it also makes it straightforward in many cases to debug, because you can actually hear the contents of those tones. It's very transparent. The surface is there for you to look at. And particularly in the IoT world, the fact that sound communication is not regulated, not subject to the same restrictions as radio frequency communication, means that it suddenly opens up these wireless communication possibilities in places that they wouldn't have previously been allowed, thinking things like operating theatres, the aviation industry. In some places it's still regulated for EM. And as mentioned, sound is fail-safe. It will often be the part of your infrastructure that survives when the rest has died. PA systems will often be driven by very low voltages, which means it is very cheap to keep these things alive. So the technical overview of how data over sound works is relatively straightforward in terms of the previous analogies that we've talked about, such as a modem. So we have a set of data, which might be a string of integers. We take that information and we encode it as acoustic parameters, which could be a series of frequencies, higher frequencies being higher integer values, and then at a receiving end, that information is heard simply by a microphone, nothing more complicated than that, and then demodulated. So a listening device decodes it into the original integer values. What a industry standard data over audio protocol would also do is add a few more elements, such as error correction. Similar to a QR code, if you cover up part of a QR code, you can scan the remnants because it has error correction. This allows you to fill in the gaps effectively, which makes it resilient to noise and robust to noisy environments, because clearly industry is a noisy place. You need a communications platform which is going to work reliably even in the presence of 100 decibel turbine noise. And it is possible to do that by selecting the right parts of the frequency spectrum and designing your algorithms for with robustness in mind. Here is a visual example of how audio might be encoded, very simply taking an audio waveform which scrolls from left to right and encoding a series of ones and zeros as loud and quiet values in much the same way as Morse code. We've talked a little bit about the applications already. Machine-to-machine information exchange is probably the most relevant to the audience here today. So thinking about a situation in which you've got 100 robots on a factory floor that moving around, it's often beneficial for them to interact with their neighbours to broadcast their status, or with a human operator, or perhaps going beyond that, sending information over a PA system that can then broadcast information to that entire factory floor, perhaps setting some configuration, resetting, or even shutting down for the day, which would be a form of rich data alerting. And another use case we're going to think about a little bit today is by taking audio which is not audible to human ears. So it's still using sound, but it's sound that is so high frequency that it's no longer within our hearing range, what we call ultrasonic audio. And this is quite powerful for use cases such as creating a proximity beacon in which your tablet, say, could be broadcasting your ultrasonic ID as you walk around the space, and nearby microphones can then detect your position as you walk from room to room. There are constraints, of course, as with any networking technology, the biggest of which is the range of the technology. And the analogy to be thinking about is basically, could I hear it? Could I speak to someone over this range? Sound-based communication operates over the same constraints as me speaking to you, meaning if I was whispering, my volume is low, so the range is small. If I'm shouting, the volume is high, the range is big, it can be 5, 10, 20 meters. Then, of course, there's amplification. So if you played a data encoding tone over a public address system such as this, then you can be transmitting over kilometers, potentially. The other constraint operates on the transmission rate, of which we're not looking at RF frequency rates here, because acoustics is by nature quite banded and there's a lot of background noise. We're looking at the order of 50 to 100 bits per second over speaking range for a protocol that is robust, you know, several nines of robustness. If you're looking at shorter ranges, you can then increase the throughput by orders of magnitude. But these are the kind of the constraints. You have the transmission rate and the range, which are kind of playing off against each other. As mentioned, it's important to design your protocols and algorithms for background noise, because the real world is noisy, and it's not just noisy, but it's reverberant as well. So if you play a sound, it echoes into the environment, and we need to compensate for that. And we also need to avoid crosstalk between different communicating devices, and we can do this by simply sending audio at different frequencies. So we can have 2 to 3 kilohertz for machine A, 4 to 5 kilohertz for machine B. The analogies from radio frequencies stand up pretty solidly if you think about broadcasting on different radio frequency bands. We're now going to move on a little bit into a series of more concrete case studies, and these are studies that we've performed with EDF Energy, for whom we've been performing some proof of concepts to explore the benefits that they might be able to reap in their power stations using acoustic communication. Before we do so, I realise I've actually failed to include any examples of what this sounds like. Because it is audible, it's probably quite somewhat informative to play you a brief sample of what a chirp, as we call it, sounds like. So I should be right playing this into the microphone, I think. So this is a short chirp which, if my hue lights were here, would turn the lights to red. So you hear it's a short series of tones. Each of those tones corresponds to an integer that then gets decoded as a command. If you want to see more of this, we have a chirp booth and a whole bunch more exciting demos. So the 3 case studies that we're going to look at for the rest of the talk. The first is about remote sensing, so capturing information from a remote sensor device. We're going to look at location tracking and operational data capture, if we have time, by operators who are going to be surveying information, moving from site to site and capturing data, then relaying it using sound. So the first case study that we're going to talk about is a really key issue, particularly in these plants with a lot of moving parts, physical moving parts, turbines and the likes, where radio frequency communication is prohibited. The objective of this study is to capture real-time data readings from sensors which might be in quite hard to reach out-of-the-way locations, dark places along a pipe or behind another piece of machinery, and to convey those readings back to a data logger in a centralized point, which then will be connected to the wider network, the wired network of the infrastructure. And the data rate, we're looking at 1 floating point reading per minute, roughly. It could be more, but the critical thing is that we want to be communicating from many sensors to one data logger, and to do so in a way that is robust, it's reliable, doesn't require a line of sight, and doesn't use any radio frequency communications. And there are multiple challenges in the current scenario, one of which is the fact that there are very few of these networked access points. Another is that these locations are hard to reach and often out of line of sight, which makes it challenging to use technologies such as Li-Fi, which requires reasonable line of sight. Cabling is very expensive to lay down in these scenarios, and also critically, often what we're looking to do is sample data for a short period of time and then relocate the unit. This isn't necessarily for kind of longitudinal studies. It might be to sample data from a few different points. So it's powerful to be able to move these sensors around quite frequently. And as mentioned, RF is prohibited due to regulations. So the solution that we've been trialing effectively takes sensor data, passes it through an analog to digital converter, and feeds it into, for our prototypes, we're simply using a Raspberry Pi computer that then plays that information over a chirp, over audio, into the environment. And these are over distances of 5, 10, 20 meters. This data then needs to be collated and captured at a data logger that is then relayed into the wired network. And there's a little bit more detail, which is that there's a requirement for there not to just to be one sensor per data logger, but several, which requires different frequency bands, basically. And the solution that we've been prototyping there is an attempt to do automatic probing, so that the data logger will broadcast into the environment, say, hey, what devices are out there, what sensors are out there. Then each sensor can flag back, it can send a chirp back saying, I'm sensor 1, I'm detecting vibration, I'm on the 2 kilohertz band, and one by one they can then kind of dial in. So you have an automatic probing mechanism. So this short video gives a visual example of how this is working in rough and ready prototype form. So what you're seeing here on the right is an analog sensor. Top left is a Raspberry Pi, which is taking the readings from that sensor. And it's then feeding them to the bottom left into a speaker, a standard consumer portable speaker. And what that speaker is playing, except you can't hear it, is ultrasonic. It's playing ultrasonic audio that then relays those readings to this mobile phone in the center of the image. And the mobile phone could be a laptop, it could be a tablet, anything with a microphone can receive that data. And as you can see, well, you would be able to see, it's also in airplane mode to show that there is no hidden connectivity between the devices. All of the information is being sent as audio. It's just audio that we can't hear. So what's beneficial about this for the client, for EDF? The key thing is that Wi-Fi was simply not a plausible platform to use in these environments beforehand. We've effectively created a wireless link between devices that simply wasn't possible before, and that means that it's a great alternative to cabling because the costs are substantially lower, and measurements can now be obtained in real time. So the sensor can chirp to the data logger is wired in to the wider network, and that means that the analysts can then see very quickly if something is going wrong. That then enables them to say, okay, we're getting interesting readings here, we'll leave the sensor here. This one, not so much. We're going to reposition and reassess, cutting the cost and the number of sensors that need to be deployed, and also opening the door to the potential for starting to do big data analytics on the information that comes out of the plant. And this is quite a big deal because the greater the number of sensors that are feeding information into the systems, the greater the volume and richness and breadth of information that can be extracted, analysis can be performed, and the greater predictive power over failure cases, which is a big deal when downtime is so costly. The second case study that we're going to look at is location tracking, which is quite a different problem set. It's also in an environment which is RF restricted, which is why technologies such as Bluetooth are forbidden. The problem that EDF are having is that it's simply not possible currently to track the location of plant operators as they're moving from space to space because of all of these technological conditions. And this makes it quite difficult to do real-time deployment of resources. The solution that we've been prototyping then is to equip operators with tablets which emit an ultrasonic identifier. So similar to the solution that we saw with the sensor reading prototype, every single tablet relays the operator's ID regular intervals into the environment as they walk from room to room. The fact that a speaker can then play into the room and be only heard in that room means that you're effectively localizing the position of the operator. There are a whole cluster of benefits from this, of course. Number one is that the operator location can be monitored in real time. Number two is that the operators also don't need to keep tabs of their own position as they're filling out information, monitoring plant conditions. That information is automatically pre-populated. That reduces human error. It also helps in a very general sense with resource coordination and time tracking. And finally, there's a rarer but very critical potential here, which is to do automatic evacuation tracking. If there does turn out to be a problem, then personnel positioning can be tracked very closely by using these ultrasonic beacons. And the final case study that I'm going to talk about is kind of connected to this, and I'm going to just have to skip over this a little bit due to time, but as these operators are moving from place to place, they're often also needing to stay in sync with their peers and neighbours, so they'll be working alongside each other to read bits of information, and it's hugely beneficial for them to stay informed in real time about what their peers are doing. But these environments are noisy, they're spatially distributed, and again, RF restrictions makes it very challenging for them to keep their data sets in sync. So the solution that we've been deploying is to create acoustic links peer-to-peer between these tablets, so an incremental status update. As information is filled out on the tablet, it will then chirp its status out into the environment, and anybody nearby can receive that incremental change, and synchronization happens automatically, basically. There's no manual intervention. Again, time and cost savings, in that if readings need to be cross-correlated, that can be done quickly and automatically. Again, in general, the time and efficiency savings that kind of trickle down across the organization. So, to sum up briefly, the status of the work that we've been doing has been very positive in the proof of concept stage. We've concluded some feasibility studies, and we've had a great substantial amount of buy-in from the team at EDF. So our next steps is to begin working with the rotating plant dynamics group, in which we'll be beginning some on-site trials in which we'll actually be deploying in the real working environments where these sensors are taking place. In the wider world, I'd like to talk really briefly about how, obviously we focused on this particular radio frequency regulated use case, but there's a whole plethora of other interesting ways in which acoustic networking can be a powerful tool for the IoT domain. One of which is, as we talked about, being able to broadcast rich data across an entire factory floor or a working plant using a PA system. It's a powerful tool to be able to take an offline device and put it online by communicating things like an authentication code to a previously unconnected device, piggyback it onto the network by effectively giving it the Wi-Fi access token. And also to create air-gapped secure zones between your connected environment and your secure zone, in which you might have some computers that you don't want to be connected using, more traditionally hackable technology. And I think underlying all of this is that because acoustics has this heritage of being pretty bulletproof, it's very tried and tested, it's very low tech, that means it's almost like a lowest common denominator fallback for connectivity. And as the number of devices, the number of connected devices continues to rise exponentially, it becomes increasingly important to have this simple basic communication medium that can always fall back on when more complex solutions fail. So we've taken a look at a few different case studies. We've looked at real-time sensing using acoustic networking. We've looked at location detection and data capture, and talked a little bit about how sound simply works. It works and has always worked, and we're really keen to start bringing these connected devices back into the age of acoustics. Thank you.